Welcome back. All right, so we took some time to talk about, well, where does this molten material, magma, come from? And we focused in on it comes kind of from the upper mantle area, so kind of the upper mantle to the crust or in the crust, so somewhere in there, from the crust, upper mantle, or upper mantle. Now, the reason that's important is because where that material is melted will ultimately give us different composition of magma, which when that magma cools to create a rock, it will thus give us different rocks. Or when that molten material erupts to the surface as lava, when it cools based on its composition, based on where it's melted from, it will give us different igneous rocks. So let's talk about that, shall we? So crystallization is the process in which igneous rocks form. It's the process in which mineral grains form and grow in cooling magma or lava. Another variable in the different types of igneous rocks is the rate at which the material cools. So the rate at which lava or magma, in this case, cools. Does it cool quickly or does it cool very slowly? So if liquid hot material cools very quickly, then you're going to get crystallization, so a rock that's formed with very, very small crystals. Whereas if a molten material, a molten body of magma cools very slowly a long period of time, you're going to get larger crystals. Think about ice. All right, let's say I put a cup of just water in the freezer. If I check it after an hour, as that material's cooled down, I'll have little ice crystals. If I check it one day later, I'll have a big ice crystal, big chunk of ice. Well, same thing here. If you get this hot stuff cooling down, if it cools down very slowly, only for a short period of time, it's only going to have small crystals. If it cools over a longer period of time, the crystals are going to get bigger. Well, that helps us determine, well, has this igneous rock formed inside the earth, where that process would be very slow to cool, or did this igneous rock form at or near the surface, where it would cool very quickly? And we could look at, one way that we can do it is look at the crystallization, big or small crystals. And that gets into the texture of rocks. So the first texture of igneous rocks, I should say, we'll talk about is aphanitic texture. Breaking down words sometimes helps me understand what they are. So these are kind of Latin-derived words, a meaning not, phaner meaning visible. So these are igneous rocks that have a texture where the crystals are not visible, at least to the naked eye. These are known as volcanic or extrusive igneous rocks. They crystallize very rapidly on or near the Earth's surface. Again, they create very small crystals that are not distinguished by the naked eye. You can see them under a magnifying glass or under a microscope. But any igneous rock that has a small crystal texture to it, an aphanitic texture, indicates it cooled at or near the surface. Some extrusive igneous rocks, extrusive meaning they've exited the earth and cooled on or near the surface, include rocks such as basalt, andesite, rhyolite. You'll hear these terms throughout this lecture, the assignment, and lab. So again, you get some extrusive rocks. Darker ones are known as basalt, on the lighter end, rhyolite. And this actually goes into, and we'll talk a little bit, I guess right now. So remember, the mafic material, so this darker material, this comes from a little bit deeper down, so kind of more in the upper mantle, where that melted material is higher in things like iron and magnesium, which are just darker elements, thus giving rocks a little bit darker color. Whereas rhyolite come from melted crustal material, continental crustal material, so a little bit higher up. Continental crustal material, a vast majority of crust is silicon and oxygen, which by nature are lighter in color. So rocks that have minerals that contain that material are also lighter in color. So felsic, a little bit higher up. So you can not only tell where the rock formed, in this case on the surface, but where that molten material came from that formed these rocks. So the opposite of aphanitic texture is a phaneritic texture. Phaner, again, that kind of Latin-derived root meaning visible. So these are also known as plutonic or intrusive igneous rock. They formed inside the Earth. So they crystallize below the Earth's surface, so they do so very slowly, which allows them to grow larger crystals, and the different kind of mineral crystal grains can be seen with the naked eye. Some common intrusive igneous rocks have names like gabbro, diorite, and granite. So again, these are forming from molten material, magma in this case, that cooled and solidified inside the earth. Gabbro is mafic, so it's a mafic, intrusive, phaneritic igneous rock. You can put all these words together. So it's darker in color with the bigger crystals. Granite is a felsic, intrusive, phaneritic igneous rock. So felsic, lighter in color, came from melted crustal material, intrusive, formed inside the earth, phaneritic, bigger crystal structure. You can kind of pick out the different mineral crystal grains here. Rhyolite and granite, they're made up of the same stuff. Basalt and gabbro, made up of the exact same stuff. It's just one cooled at or near the surface, one cooled below ground. So again, here's kind of a side-by-side, aphanitic, not really visible to the naked eye. If we put this under a microscope, we would be able to see some crystals. This is rhyolite. Phaneritic, visible crystals. You can pick out the white, the black, the pink. You can pick out these different mineral crystal grains. But again, rhyolite and granite are actually made of the same exact stuff. It's just one cooled below ground, so it has bigger crystals. One cooled at or near the surface, so it has smaller crystals. So we have aphanitic, phaneritic, and then kind of an in-between called a porphyritic. It has both intrusive and extrusive characteristics, and it goes through two phases of cooling. Stick with me now. Initially, kind of magma made its way up, and it started to cool below the ground. So it just stopped and it began to cool, and so some minerals started to grow and grow big. But the whole magma body did not cool and crystallize. It was still melted material, but there's some minerals in there started to form crystals. And then for some reason, kind of from below, that something below said, you know what, yeah, magma, let's just continue our way out. So that magma body then gets pushed closer to or onto the surface, so the rest of that molten material cooled very quickly. So you get this mix of kind of bigger crystals that cooled when that material was underground, and all of a sudden that material gets pushed above ground and everything else cools very quickly, so it's smaller crystals. So you can really distinguish porphyritic texture because they have this small and big crystal texture. Some common porphyritic texture rocks would be considered andesite porphyry, rhyolite porphyry. So kind of both small and big, two-step process. So here you can see rhyolite porphyry, so that you can see the kind of the pinkish stuff that's more indicative of rhyolite, but you can also see some of these bigger chunks of crystals, making it porphyritic, so rhyolite porphyry. Same with andesite. Andesite's an intermediate extrusive igneous rock, so it's typically smaller, kind of grayish, smaller, not visible grained igneous rock, but then you'll have these black, bigger crystal grains that signifies the cooling began below ground, but then the cooling finished above ground. So you get this mix of small and bigger crystals, and this would be andesite porphyry. So we have aphanitic, phaneritic, porphyritic, and you can pick up an igneous rock and say, oh, because of this texture, this is a story. So these rocks tell a story. Some other textures that help of igneous rocks to help tell a story is a glassy texture. I'll show you what that is here momentarily. It's when lava, so extrusive, so molten material on the surface, cools so rapidly that no crystallization can occur. It results in a naturally formed amorphous glass with very few to no crystals. Obsidian is an example of this extrusive igneous rock with a glassy texture. And then vesicular. It gives an igneous rock, it looks like it has air bubbles in it, vesicles. So it's the result of trapped gas in the molten rock at the time of solidification. So a lot of times this material extrudes from a volcano, whether it flows out or it's blown out. It has a lot of trapped gas, and this material cools very quickly once it's exposed to the air, that you see these trapped kind of air bubbles in there. Some examples of an extrusive igneous rock that has a vesicular texture, something like pumice and scoria. So glassy looks like glass, oftentimes broken chunks of glass. This is obsidian. Vesicular, you can kind of see these little air pockets in here. They have vesicles. So again, they tell a story. They tell a story. Let's see what else. How much more we got here? Yeah, we can finish. Yes, let's keep going. Sorry. So we can look at the texture to kind of tell where it formed, but then we look at the composition, the chemical makeup of it to figure out, well, where did it start? Where did this molten material melt from? From the crust, from the upper mantle, or somewhere kind of in between them, between the mantle and the crust. So igneous rocks are further subdivided based on chemical composition, and a lot of it's tied to silica content, how much or how little silica, quartz, amongst other things, are in these. And I mentioned some of these terms. I mentioned them also back in the previous section, but felsic, a felsic igneous rock has that's a chemical composition. It's a rock rich in silicate minerals that contain lighter elements such as silicon, oxygen, aluminum, sodium, and potassium. These lighter elements are, since they're lighter, they're going to be further up in the earth, so in the crust. They're also lighter in color. So when you're looking at an igneous rock that's kind of lighter in color, like pinkish tones, orangish tones, white, things like that, that would indicate a felsic igneous rock. Not only are the elements in it lighter weight-wise, but the color is also much lighter. So the color itself indicates chemical composition, which in itself indicates where this material melted from. So felsic igneous rocks formed from melt material from the crust. Then intermediate, a little bit further down. Well, let's go jump down to mafic. Mafic igneous rocks are not rich in silicate minerals, and they contain heavier elements like magnesium, iron, calcium. This material, since it's heavier, comes from a little bit further down in the earth, so kind of that upper mantle area. These elements are darker in color, therefore the rocks are also darker in color. So you see a dark igneous rock, it's most likely mafic, and what that's telling you is that formed from melted material a little bit further down, kind of down towards the upper mantle area. And then so in between felsic and mafic is the in-between called intermediate. It's kind of a good mix between the felsic and mafic, so it's in between light and dark, oftentimes kind of like a grayish color, somewhere right around there, but a good mix of lighter and dark colors, making it gray. And so that indicates where the molten material comes from, again, kind of between the crust and the upper mantle, right at that kind of boundary area. So when we start to talk about the different chemical composition, not only to tell us where this molten material comes from, it will also start to tell us, well, what kind of volcanoes can be formed from this? Basalt forming certain types of volcanoes, andesite forming different types of volcanoes, rhyolite, different kind of volcanoes, dacite, you can just ignore that for now. But kind of what these the different chemical composition makeup of the material, this molten material, will actually also give us different volcanoes, and whether it's extrusive or intrusive and how those are paired up. The minerals, going back to kind of Unit 5, which are maybe indicative of some of these things. So not only do igneous bodies create volcanoes, there's also different stuff underground, different structures they could make. You see big blobs of cooled magma can be considered batholiths. It's a little bit smaller. It's called a stock. If it's kind of a mushroom shaped, it's a laccolith. It's kind of a vertical spire. It's called a dike. If it's a horizontal little bit of volcanic material, is called a sill. Volcanic necks feed volcanoes. So there's all these different structures as well. Just kind of another look at some of those. So igneous rocks don't always, or only I should say, form volcanoes. There's these other structures that we can sometimes see in the layers of the earth. So we'll go ahead and pause there. Before we do, let me give you the first part of the super secret code. It is the number 9. You got me? The number 9. You got me? The number 9. So when we come back, we'll talk about some of the hazards associated with igneous rocks and volcanoes. So I'll pause there, and I'll see you back here in just a minute.